business is. All we're looking at, we compare two strings of ones and zeros, right? And we look at each position of the ones and zeros. However many positions differ, right, in each of these strings is the Hamming distance. So let's go through this again. To find the Hamming distance between U and V, for example 11, let's just take V and copy it under U. Write it out. So we get 0, 1, 1, 1, 0, 0, 1. Okay, now compare top to bottom each column. And you should notice that in each and every position, the numbers are all different. None of the numbers match up in the columns. So since there are, 7 positions, and none of the numbers match in any of the 7 positions, these two strings have a Hamming distance of 7. Okay, do you remember that? Hopefully. We've got to keep this in mind for the next couple of examples. Now, nearest neighbor decoding. Here's what's going on. For any word, group of numbers, you have these strings of text, block codes, so on and so forth. Well, sometimes things go wrong. Sometimes the cell tower goes down, like right in the middle of you sending a text, and something doesn't get translated correctly. Well, there's code that's built in. So say you have something like this, and we'll do the specifics for this example here in a bit. Say you have one word that codes like this. Okay? And say you have the next word in progression that codes like this. So you can see that these two words or strings, these are not the same, right? Well, depending on how many errors there are, we're talking about nearest neighbor decoding, however many errors there are, if the number of errors puts you closer to this word, it defaults to this word. If the number of errors puts you closer to this word, decoding will default in this direction, whichever one it's closest to, which means whichever one has a shorter Hamming distance is where it defaults. Make sense? That's why it's the nearest neighbor. You go to the closest code. So that's what's going on here. And the key thing about this, if there's more than one possible answer, you won't catch the error. And your text message or whatever it is you're trying to send will just be messed up. There's no way to fix it. All right? Next. Key things to remember. With error detection, the code will detect m minus 1 or fewer errors. Okay, let's take a look here. Suppose we have this list of codes. We've got 4 of them, right? These guys are blue. And first thing we need to do is find the minimum distance between any of them. Well, the first one, all zeros. The next line down, between the first and second code, has a Hamming distance of
3.
3. It differs in 3 positions from the first and second. And then if you compare it with the third and fourth, those differ by more than 3, right? So the minimum distance between any 2 codes, right, the absolute minimum, in this case, is going to be 3. Okay, so any message that differs from any of these 4 codes will be detected since the next closest word differs by at least 3 digits. But that message will only be caught if it differs in 1 or 2 positions, right? It's always 1 less than the shortest distance. Okay, but you can see in step 3, if the message has 3 errors, may not catch it. If you meant to send the all zeros code, but it gets transmitted with 3 errors, look at the ones, okay, that got thrown in there. Those are 3 errors, yes, but if you look at our list, it's actually one of the words. So it automatically thinks, oh, you meant to send that word. Okay. So you won't catch that mistake. 2. If it's even, it's 2 less divided by 2. Or fewer. So let's go through these examples. Example 12. 5 is your minimal distance between code words. Nearest neighbor will correct how many errors? Okay, 5 is your distance, so that's an odd distance. So you take 5 minus 1, divided by 2, so 4 over 2. This nearest neighbor detection will only correct 2 or fewer of these errors. That's just how it is. Just have no formula. Example 13, if we have a Hamming distance of 8, so a minimal distance 8 between any 2 code words, then the nearest neighbor will correct, well, 8 is even, so plug it into the formula. 8 minus 2 divided by 2, so it's going to be 6 over 2. It will correct 3 errors or less. Now remember, it can't correct the exact number of errors because in the last example we saw, you could have an actual word that matches however many errors there are. Okay? So know those formulas. Now, this example is extremely wordy, so that's why we have all of this stuff on the board. So let's have a little chat here. Okay. Say that our original word is this guy right here. 0, 1, 1, 0, 1, 0, 1, 0, 1. That's what you meant to send in your text message, right? That's how it's supposed to be coded. And say that the next word up, the closest word to it, is this guy right here. And like we said before, they are different. You can see that. Specifically, if you look at your notes, you should have a Hamming distance of 5. They should differ in 5 positions. We can check that. So copy this word over. 0, 1, 1, 0, 0, 1, 0, 1, 0. Okay, so yeah. 1, 2, 3, 4, 5. So, from the original word to the next word in your set of code, you have a Hamming distance of 5. Okay, keep that in mind. 5 is the key thing here. Well, something happened, and it got sent incorrectly, and this is what it now looks like with the errors. So, let's compare this word to the original. I'm going to write the original on top. 0, 1, 1, 0. Okay. Well, this now has a Hamming distance of 1, 2, 3. Okay. Well, think about it. If you have 3 errors, that means that everything up to that is wrong. Well, that means this word is closer to this guy. Okay. So the next word in line is the nearest neighbor. Okay, that's what's going on here. Since you have 3 errors here, it defaults to the next closest word. There you have it. But say it got sent differently, so we're back to the original, and this is the other error that got made. New scenario, let's compare. We've got 0, 1, 1. Okay. So we differ in 2 places. Okay. Since this is only 2 places away from the original, that means it's 3 places away from the next word, so this one defaults to the original. Right? It's only off by 2 instead of being off by 3. to the original, right? If you're 3 errors away, that pushes you closer to the next word in line. See what's going on? That's why it's the nearest neighbor error detection. Okay. And you can see a little chart right here. Sorry, it's a little messed up. So we've got 2 code words. Here's essentially what's going on. And the 2 code words are 3 units apart. Okay. So there's your first one, and then there's 3 more. So if you have an error, okay, the mumbling, a little annoying. If you're going to converse, please excuse yourselves and converse outside. Please. If you have one error, like this second one, right, that error is only 1 off from the original code word on the left, so it will default to the code on the far left, the original. If you have 2 errors from the original here on the left, well, that one's closer to the next word in line, so it defaults to the right. Same idea down here with the second chart. 2 code words, 4 units apart. If you have 2 errors, you're kind of stuck, right? Because it can go your way, right? But if you only have 1 error, you're closer on this end, so it defaults to the next code. You only have 1 error from the original on the left, it will default to the code on the left side. This is why it's called nearest neighbor. You choose the closest code according to your hand distance. Possible exam question. Give me a second to get that copied. And then we're moving on. Some of you have probably seen matrices before, right? So here's an actual application of them. Recall the definition for parity of a string, right? Parity tells you whether you have an even number of ones in your code or an odd number of ones in your code. We did an example on Monday where we used the parity of a string to determine the check digit. Okay, we're going to do a little bit more of that today. We're going to do a little bit differently though. So say we have those guys, right? For B, A, and T, add your parity check digit to the end. All right, so for B, you have 2 ones. That's an even number. So if you look at the code directly beneath it, you'll notice there's an extra 0 on the end. Okay, so here's your check digit, even number ones. Same thing for the letter A. Look at the code immediately beneath that. Again, there's another 0 on the end. And then for T, there's 3 ones in the code for T. So it should have a check digit of 1, and you can see in the code directly beneath it, it appears at the end of the string. Here's the other way of determining your check bits, or your check digit when we're talking about parity. Remember, with 1s and 0s, binary code, we're working in base 2, right? Only 2 numbers, 1s and 0s, which means we are dividing our sums by 2, and we only look at the remainder, okay? So we're kind of bringing all this full circle. So for the first code, if you add all of those numbers together, yes, 1 plus 1 equals 2, but in binary, 2 divided by 2 is 1 with a remainder of 0. We're only looking at the remainder. That's why it has a parity check digit of 0. Same idea for the next one. 1 plus 1 is equal to 0 in binary. And for the last one, 1 plus 1 plus 1 gives us 3. 3 divided by 2 has a remainder of 1. That's why you get a check digit of 1. You're kind of remembering this? Modular arithmetic, right? We're working in base 2. All right. The only problem whenever we work with parity check digits like this is, say we have this string, 0, 1, 0, 0, 0, 0, 0, 1, 0. All right, there's 2 1s in there, right? Well, say a 1 and a 0 got flip-flopped in position. You still got 2 1s though, right? So it doesn't change the parity of it, so you won't catch an error. Make sense? The check digit doesn't change, so there's nothing to tell you that something actually went wrong. All right, well, to fix that, you can add more check bits. Add a couple other numbers in there. Promise it works. And unless told otherwise, we're going to use this formula. So, the numbers in your message or in your original code will be denoted with the letters M, M1, M2, M3, okay? And your check bits, your new check digits that you tack onto the end, will be denoted as C1, C2, C3. Here's how you calculate your check bits. Okay. And again, we're working in base 2. It's all binary. It's only 1s and 0s. We only look at the remainder when we divide our sums by 2. Okay. So for the following examples, we're going to look at a 3-6 block code. How many, if we write it that way, here's a little review for notation, 3, 6. 3 tells us what? What's the 3 stand for?
The rows? The rows, the amount of rows?
Nope. This is the original code. It means that there were 3 values in your original code, and then once you add your check bits, you now have 6 digits in your code. You can see that in the notes from, I believe it was Monday. Monday. Okay. Calculating our check bits. So we have the original message, 0, 1, 0. Okay. That means the first letter in our message, M1, is 0. The second letter in our message is 1, and the third letter in our message is the 0. There's M1, M2, M3. Right? Plugging into the formula from the previous slide. So to calculate the check bit, the new string of digits that gets sent. Okay. Questions on calculating or check bits? Follow the formula. Okay, so here's our 3 formulas for calculating your check bits. Alright. So in this example, our original message is 010, so according to this, the first digit, 0, is M1. Second digit, 1, becomes M2. Third digit, another 0 becomes M3. And then just follow the pattern. You add M1, M2 for your first one, follow the cycle, and then it goes M2, M3 for the next one. For the last one, you finish the circle, M3, come back around and add it to M1. Okay, now I have to introduce this idea of matrix. We are talking about matrix codes. Okay. Since we're working with essentially a lot of ones and zeros, we can organize them in a particular way using what we call a matrix. Okay. Here's a couple examples. Okay. We use the elongated brackets to show that we are enclosing this group of codes. And we always name our matrices, or we denote the size of the matrix according to rows and columns. Okay, so the size of the matrix. It's always row by column. Okay. So if we have this first matrix, it has 3 rows, 2 columns, so it's a 3 by 2 matrix. Similarly, for the next one, there are 3 rows, 6 columns, so it is a 3 by 6 matrix. We label it top to bottom and left to right. So rows are labeled top to bottom, columns go left to right. Always and forever, that will never change. And with matrices, we have to have this idea of an identity matrix. So you'll notice, look at the size of each of these matrices for A, B, and C. Since the rows and columns are the same, your identity matrix should always be a perfect square, right? So for a 2 by 2, things to keep in mind. You have 1s along the diagonal and 0s everywhere else for the identity. So for a 2 by 2, you would have a box. You have 1s on the diagonal and fill in the 0s everywhere else. All there is to it for the identity. Bless you. 3 by 3, same thing. If it's a 3 by 3, you should have 3 1s along your diagonal. So 1, 1, 1. Fill in your zeros. And 4 by 4. 4 1s on the diagonal. Fill in your zeros everywhere else. Okay. Relatively painless so far. All right. 1s go on your main diagonal, right? Left to right. Fill in zeros everywhere else. So that's the identity matrix. Now, we have to take this a step further, and we have to look at what we call the generator matrix for our block code. So for now, we're going to keep this relatively straightforward. We're still working with this 3 by 6 code, right, or 3-6 block code, excuse me. Which means you're going to have to create a 3 by 6 matrix. Now you'll notice across the bottom, row 1. Okay, so we're going across the rows. The first check bit for row 1, so we're only looking at the top row. Follow the pattern. You take M1 plus M2, just row 1. I don't care about the bottom two, just the top. Well, the values in positions M1 and M2, 1 and 0, added up, you get 1. Let's go to row 2 and calculate the first check bit for row 2. So we're looking at the, like I said, second row. We're still doing C1, so add M1 and M2 together. 0 plus 1 gives us another 1. First check bit for the third row would just be 0. 0 plus 0. Let's do the second check bit for row 1. So for the second check bit, C2, you take M2 plus M3. So our second check bit for row 1 would just be 0. Do the same thing down the line for row 2. Second check bit, man, it's so hard to say fast. 1 plus 0 gives us a 1. And for row 3, another 1. Is this clear where this is all coming from?
No.
Okay. We are lining up our columns. We've got 3 strings of code. Right? Row 1, row 2, row 3. Each row represents a string. And for each row, there's 3 positions, right? So you've got the column of all of the M1s from each of your strings, the column of M2s for each of your strings, and the column of M3s for each of your strings. We are calculating the check bit for each individual string. We're going all the way across. Okay? So let's look at check bit 3. So we're using this formula for C3. And we're only looking at the top row for that last digit in the top corner. So across the top row, what numbers are in positions M1 and M3? Just the top row. 1 and 0. So, following formula. 1 plus 0 gives you 1. So 1 is your third check bit for row 1. We're working down the line. Okay, row 2. We're still calculating the third check bit. Third check bit. Row 2. We need the values in positions M1 and M3 according to the formula. M1 and M3 is 0, 0. So put together, third check bit is 0. Now we're on the third row, our third string of code. We're doing the third check bit for the third string of code. Still the same formula, M1 plus M3 gives us a 1. 0 plus 1. How are we doing? And it's getting a little clearer. Hopefully, maybe possible. This is why we'll have to do next week. Okay. Now we have to find the generator matrix for comparing check equations. All right. For this one, we're going to do a 3 by 5 matrix. Okay. So that means our original code has how many digits? The original. 3. So we have 3 in the original. Okay. Here's our formulas for how we calculate our check bits, C1 and C2, right? You start with 3, you end up with 5 digits, so you have 2 check bits or check digits. Since we have 3 in our original string, that means we have to work with a 3 by 3 identity matrix. Let's start. Okay? So we write this out. Since it's a 3 by 3, 3 ones on the diagonal. And that means we're going to have 2 more columns. So let's label this. This is M1. 2 more columns for the check bits. So this will be C1 and C2. Okay. For C1, we're going to do all of the first check bits for each of the 3 rows. So the first row, 1, 0, 0. What's the first check bit according to the formula that we gave you up here? Add M2 and M3, 0 plus 0 gives us 0. Okay? Second row, next one down. 0, 1, 0. Calculate the first check bit for the second row. 1. M2 plus M3, 1 plus 0 is 1. Exactly. And first check digit or check bit for the third row will also be 1. How are we doing so far? Is this getting clearer where this is coming from? Okay. So that's the first check digit for the 3 rows. Now we're going to do second check bit or check digit for each row. Okay, so we're using the second formula. First row, 1, 0, 0. Calculate your second check bit. M1 plus M3 is 1 plus 0, so we get 1. Okay. Second row, calculate the second check bit.
0.
M1 plus M3 would be 0 plus 0, so it's still 0. And then for our last row, M1 plus M3, 0 plus 1 is 1. You have successfully constructed the generator matrix of a 3-5-5 matrix code using those 2 check equations. Typically, we will tell you which formulas to use to calculate the check bits. Now, we have to be able to apply this generator matrix. Okay. Find the translated code word for the message 101. Okay, so that's the word we want to send. And this is the generator matrix that we figured out. All right. What to do? Write the message you want to transmit down the side of the matrix. All right. So we want to send 1, 0, 1. Ignore that little A in parentheses. I don't know what that's there. I don't know how that showed up. Okay. Then we're supposed to, according to the directions, add the rows that have a 1 in the original message. So if it's originally 1, 0, 1, we're only going to add together the top row and the bottom row, because the original message, there's a 0 in the middle, so we don't add the second row. We should say the original message. Which in this case is 1, 0, 1. And that's why we are not even going to bother looking at second row. Are we good so far? From here, it's just adding top to bottom. All right. Good old modular arithmetic in base 2. Top to bottom. 1 plus 0. Remember, we're cutting out that second row. Top row plus bottom row. 1 plus 0 gives us 1. 0, 0 gives us 0. 0, 1 gives us 1. 1 and 0 gives us another 1. And another 1. And the last one should be a 0. 1 plus 1 is 2, but we're in base 2. So 1 plus 1 becomes a 0. 0. So that means this is how your original message, 101, is encoded. You're using your generator matrix to actually encode your message. So if you want to text somebody 101, hypothetically, this is what happened. There'd be a code built into your phone that 21 possible words, right? Because, you have your original word. Sometimes an arrow goes wrong. It's got to default to another word, right? Has to figure out which one is actually correct. Well, write your possible exam question first. It's going to come back. Hold that thought for a second. Okay. So while you're writing, since we now know how to encode a single string, the next thing we have to do is figure out, well, what are all of the possibilities that you could have? Because remember, something could go wrong, so you have to have your list of possible code words that whatever message you're sending has to default to. It has to have a backup. Gotta get that news. Give me like 7 minutes really you can watch your news. Anybody still writing? 1 second. 1 second. Anybody else still writing? So, now we gotta find all the possible code words from a single generator matrix. How do we do this? Well, we have to consider all of our possibilities. This is going to be 2, 5 code word. Here's how you can tell. See the ones on this diagonal? It's a 2 by 2 identity matrix, right? 2 by 2 identity matrix with 1, 2, 3 more check bits. Okay. Always look for those ones on the diagonal. They're going to come first. Right? So if you had 3 ones on the diagonal, it would be a 3, 5 instead of a 2, 5. We'll go more in depth with this on Monday, don't worry. But for now, we have to figure out all of our possibilities. So you have 2 in each string, 2 digits, right? Because it's a 2 by 2 matrix, there should be 2 digits in each of your strings. Now, how many possible strings can you make? Well, the first one, you could have a 0 and a 0. You could also have another string that is a 0 and a 1. Or you could have another string, if you flip-flop it, that's a 1 and a 0. Or you could have another string that is all ones. So these are 4 possible code words. You know there's only 4 possible code words because you only have 2 digits with which to make your code word. So these are all of the combinations that you could have with only 2 digits. Okay? So that means we take each individual code word, apply it to the generator matrix like we did in the previous example, and that's going to pop out 4 possible encoded words. Here we go. So let's start with this group. We'll call this A, B, C, and D. We're going by columns, right? Column 1, this is code word A. So let's see how this lays out. All right? So we take our matrix, and we lay out our values for A, put it next to it. We get a 0 and a 0. in that first position, right? So we won't use the top row, which only leaves us with the bottom. So for code word B, after you use the generator matrix, it's just the bottom row. 0, 1, 0, 1, 1. Okay. Next one. Code word C. Our digits are 1, 0. So write them to the side. Okay. Well, there's a 0 in the bottom row of our message, so we only look at the top row. You only take the rows that have a 1 that corresponds to it in the original message. So the top row is 1, 0, 0, 1, 0. Okay, now for the last one. For row D, or letter D, we've got 1, 1. All right, since both of our rows, top row and bottom one, have a 1 corresponding to them from the original message, you have to add top to bottom rows 1 and 2. So from the top, 1 plus 0 is 1. 0 plus 1 is 1. 0, 0, 0. 1 plus 1 is 0.